So today we're going to bag another couple of Aussie X strips, and I'm going to talk about propellers. We're at Maryborough today, which is we're still in Queensland. This is about 45 or 50 miles north of Gympie, which is where we left off, and we're going to fly north probably another 50 or 60 miles to a strip called Mondurun, not sure how you say that, and then maybe onto Hervey Bay. And I'm going to talk about the props as we go. So the first thing you need to know about this aeroplane is it has constant speed propellers, and because everything else pretty much follows on from that, it's probably worth spending a bit of time reviewing what that means. So you're probably aware that the blades of a propeller have an aerofoil section just like a wing, and so they generate lift as they spin, and because the propeller is mounted vertically, we call that thrust instead of lift. But there's an immediate problem with a fixed pitch propeller, such as the one you've got on your Cessna 172, let's say. So if you imagine the aircraft standing still and the propeller spinning through the air, the angle of attack of the propeller blade is just the angle that the blade's offset from the vertical. So the airflow is this way. Now the problem is, as soon as the aircraft starts moving through the air, there's a component of the airflow now goes this way. So the relative wind, instead of being just in the vertical direction, is now in a sense inclined this way, and of course you can see the angle of attack diminishes. And in fact, at some point the angle of attack will be zero, and that means the blade will be producing no thrust at all. So you can see that the prop's effectiveness changes with speed, and in fact there's only one ideal angle of attack for a propeller, and everything else is a compromise, assuming a fixed pitch propeller. And of course that's why we have a propeller where we can vary the angle of the blades during flight. And so having a propeller that can vary the blade angle on the go means that we can increase the angle as the speed increases to maintain the same angle of attack. That angle of attack of the propeller blades to the relative wind, remember, not the angle of attack of the wing. And because the angle of attack varies in proportion with the RPM, we generally set a given RPM from the cockpit using the prop lever, and this is maintained by a device in the propeller hub. This is called a governor, and this works by increasing or decreasing the blade angle if the prop speeds up or slows down, thereby maintaining a constant RPM. So that's a very simplistic account of how a constant speed prop works. In practice we use this to set various RPM settings for different phases of flight, and we know the ideal settings because we read them from tables in the flight manual. And in fact, so we got a bunch of tables. These are just printed out from the Twin Otter, Aerosoft Twin Otter manual. Now the Twin Otter uses the built-in FSX propeller system, so it inherits all the pros and cons of that system, but it is by and large a passable simulation. You can see the effects of different prop RPM settings by monitoring the fuel flow gauges. So there is a genuine effect on fuel economy, and that's one of the reasons to pay attention to the prop settings. Now you recall that I said the governor maintains the RPM by varying the blade angle, and of course this has other consequences. So for example, the engine has to work harder to spin the prop when the blade angle is higher or coarser, and the limiting case of this is if we were to feather the props, which means that they're perpendicular to the oncoming air, or in other words they're flat onto the direction of rotation. And this is why you see the torque gauge rise as we select a coarser pitch. So it's conventional to increase the RPM setting before adding power, and conversely when we're making reductions in power we reduce the power first and then select a coarser or higher blade angle. And particularly when we're increasing power, this helps us avoid over-torquing the engine. So the net effect of this is we're maintaining a balance between 5 different parameters. We've got the RPM, the torque, generated, the speed of the aircraft, the fuel flow, and also the aircraft attitude. Now some of these we can influence directly, so the attitude, by using the flight controls. The propeller RPM, we can select that directly from the prop lever. The torque, we can select that directly by moving the power lever, and the other values are consequences of the interplay of all those other ones. So the next thing to say about the props in this aircraft is they're fully featherable, and this is important in the real aircraft, particularly if we get an engine failure, because the prop windmills in the airflow and keeps the engine turning over, creating a significant amount of drag. Now this is a turboprop and it's a free turboprop, so the amount of drag created certainly isn't as much as we'd get on a piston engined aircraft, and we can feather the prop by pulling the prop lever all the way back. In fact, let's set this up so you can see what I'm doing. So we can see the results of all this on the RPM and the torque gauges, and if I just set this up so we've got a good view of those gauges. So if we go with the right engine first, you want to look at the torque gauge here, the RPM, prop RPM gauge here. This is gas generator RPM down here as well, but we're not too interested in that for now. If I just spool that engine up a little way, you can see the torque gauge rising. You can see the prop RPM is rising. This is a percentage of maximum. So we've gone to 20 psi on the torque, and we're on pretty much 100% RPM on the prop. If I go to idle, you see the RPM will drop and it will stabilise at around 60%, and we've got between 5 and 10% on the torque. Now idle torque is going to depend on things like the outside air temperature and the density altitude. Looking at the prop gauge, this green arc is the governed range, so when we're out of that green arc, it's out of the range that's under direct control of the governor. So when we're out of that green arc, the engine's basically not producing enough torque to spin the props up to the selected RPM. Now if I feather that prop by bringing the lever all the way back, you see the RPM falls and the torque rises to about 40 psi. The RPM will settle at about 20%, and that engine is now not producing any thrust at all, or negligible thrust. The blades are feathered, which means that they're pretty much flat on to the direction of rotation. And if I unfeather, the opposite happens. The torque falls as the blades are now much easier to turn against the air resistance. And the other thing that should happen is, if we look at the fuel flow gauges, which are these ones here, we should see, if I spin it up again, we're looking at the right hand one here, fuel flow rises with torque and RPM. Again, we get some oscillation and it stabilises at a particular fuel flow. So we've got torque selected to about 30 psi at the moment. We've got maximum prop RPM. If I select a lower RPM, this is giving us an increased blade angle. We'll see three different effects. We're going to see the torque increases, the RPM decreases, and also the fuel flow goes down. Now that's interesting. You might expect the fuel flow to go up because the torque's going up, but in fact what we're doing is we're selecting a more efficient blade angle. So we're getting that complicated web of variables that I talked about. So that's the basics of the constant speed propeller. We're going to talk more about the details of all of that, but for now let's get out of here. We're at Maryborough. We're going to go north to Munduran. Okay, we got that set on the GPS, 57 miles, pretty much northwest. Let's just check what the weather's doing.
Bravo, airport information, hotel 10050, weather wind 285 at 5, visibility 10.
Wind from the west at 5.
222.11, QNH 1016, advise on
1016.
hotel.
So the weather's fine, I'm not going to have any problems with the wind. There's 400 feet. We're going to be turning left onto course. And we can let the autopilot have it now. We're going to climb to 3,000 feet. So Monduran, we've got 10 miles to run. Weather's okay, so we shouldn't have any problem finding the strip. It's a grass strip, so it's not going to be the easiest thing to find, but it's fairly distinctive. It's got a bunch of buildings there as well. I've got the RXP GPS, and this is showing me usefully. It shows the crosswind, or it shows what the winds aloft are doing, and it's showing me a 9-knot crosswind from the west. I'm going to come off nav, go into heading hold, and I'm just going to give us a little bit of an arc around it so we can see the strip and decide which way we're going to land. Still on altitude hold, so the speed's coming back as I pull the power. So we've got a strip going essentially something like 2-4, so east-west more or less. We can set up for a right base here. This looks about, that'll give us the right direction given the wind. Kind of bumpy as well, you can see that up and down. Need to put some power back in. I'm going to come off altitude hold now. That will come off autopilot completely. Now this is not a particularly short strip. You've got plenty of room really. But we're going to demonstrate something else that's characteristic of turboprop aircraft, and that's the reverse thrust. That lets us stop on a particularly short strip, or even on a modestly short strip. You know, it gives us a bit of leeway if we land a bit long. Again, this is a really nice Aussie X strip, nice grass strip. It's got a nice, you know, bit of fudge-reel scenery just to locate it there. Got some buildings and a little lake there and some orchards or something going on. So we're coming in nicely. We're a little bit over 80 knots. Coming in quite steeply because this is rising. This high ground falling off towards the strip. And I think the runway is going to slope up a little bit as well after we land. Okay, we're going to start to flare gradually now. Watch out for them birds. Holding it off. And we're down. So we can go to reverse. Didn't need too much of that, we're pretty much stopped now. So what's happening here is the engines are spinning back up, but the propeller blades have been selected through, flat and into reverse pitch, so now they're pushing instead of pulling. And this is great news for short landings. We can stop in a very limited space. So to talk about reverse thrust in any detail, we need to look at the beta system. Now beta is often used interchangeably with reverse thrust, but that's not strictly correct. The beta range corresponds to those situations where the prop blade angle is between plus 17 degrees and minus 15 degrees. And if I tell you that the blade angle at idle is 11 degrees, you should see that the beta range covers part of the forward thrust range as well. Now this all gets fantastically complicated, so I'm just going to say enough about the details to put the Aerosoft Twin Otter's features in perspective. So the beta range is for ground operations, and it manages the props when the torque is low enough that the prop governor is inoperative, shall we say. So what do we need to know about this mechanism to get a bit of an understanding of how it works? Well, the blade angle is controlled by oil being pumped into a chamber in the propeller hub, and in the so-called alpha range, which covers air operations, the pressure of that oil is controlled directly by the position of the prop lever, more or less. Now in the beta range, the oil pressure in the hub is controlled by a fairly complicated tap dance between three different oil valves. There's the main prop governor pilot valve, there's a thing called the beta reverse valve, and another valve again called the beta backup valve. Now leaving aside the details, the net effect of all this is that for blade angles below 17 degrees, the prop blade angle responds directly to the power lever, and this allows faster changes of thrust for taxiing and manoeuvring on the ground. And then pulling the power levers back through the gate cycles the blade angles through flat and into reverse pitch, and then progressively as we pull them further back begins dumping more fuel into the engines, and we get progressively increasing reverse thrust. Now I've just skipped over all of that without too much detail, and that's mainly because it's not really relevant to the Twin Otter Extended. This is a theme I'm probably going to come back to from time to time because it addresses what is and isn't simulated in this package. So the beta backup system is, unsurprisingly, a backup system that's supposed to prevent us going into reverse if the beta system fails. So say if the beta reverse valve gets stuck open. And the point is there's nothing you can do in the Aerosoft Twin Otter to make that system fail. So really the beta backup system is an irrelevance and actually isn't modelled at all. In fact, there is one thing you can do to invoke the beta backup system, and that's to flip the test switch. So with the test switch in the on position, pulling the levers into reverse gives us a couple of flashing lights. Now in the real system, those flashing lights are direct feedback, showing us the blade angle cycling backwards and forwards around a limit of plus 9 degrees as the beta backup valve opens and closes. In the simulator, that's really meaningless. There's nothing actually happening under there, but it does allow us to go through the checklist and perform the test in a fairly authentic manner, if nothing else. Now you find a detailed description of some of this stuff about the beta system in the Aerosoft Twin Otter manual, but really it's interesting background reading and nothing more than that. It's not really relevant to flying the Twin Otter Extended. So losing an engine's a contingency we always need to plan ahead for, and in short takeoff and landing operations the margins are a lot tighter. Now, the Twin Otter was designed as a STOL aircraft from the outset, and as a twin we have additional factors to pay attention to. So if we lose an engine on takeoff in the Twin Otter, we're going to need to do something immediately to keep the aircraft flying. We're going to get a drastic reduction in speed and in climb performance, but we're also going to get a drastic yaw and a secondary roll towards the dead engine because of the asymmetric thrust. Now, unique to twins is a value called the minimum controllable airspeed, and this is the slowest speed we can fly with maximum asymmetric thrust and still have enough rudder and aileron assertion to counter those asymmetric thrust effects. Now, there's a couple of factors that come into play here, and the first of those is the rated power of the engines. The Twin Otter 300 series, which is what we're flying here, has PT6A-27 engines, and these are derated in the Twin Otter to 620 horsepower. Now, what that means is we have to treat these engines as if they produced 620 horsepower, even though they're capable of producing 680 horsepower. And the main reason for this is if we were to be doing a takeoff with the engines outputting 680 horsepower, or more than 620, and we lost an engine, then we're pretty much guaranteed to immediately lose control of the aircraft and crash. And the other crucial factor we need to consider brings us back to props, and that's the need to feather the propeller if we have an engine failure, particularly on takeoff. And this is why we have an auto feather system. Now, not all Twin Otters have the auto feather system. This one does, and the auto feather is important when we're doing STOL operations, and in particular because it allows us to operate close to or even below VMC, the minimum controllable airspeed, VMCA formally. That's the minimum controllable airspeed while airborne. So we're going to take a look at the auto feather system now, and I'll just set this up so we can see what's happening. So the auto feather system, this is a simple system as far as flying the aircraft is concerned. All we do is, before we take off, we select the system on by pressing the button on the panel. We get a light illuminated here to show that the auto feather is selected, and to arm the system we simply go ahead and proceed through the takeoff. Now, I can show you that in outline. So as we bring the power up, the auto feather system arms. Now, formally, I'm just going to bring that down so we can hear. Now, formally, that arming happens when the gas generator RPM rises above 86%. If you've got an eagle eye, you'll have noticed that the system armed at a lower percentage there. I think that's because in the original Twin Otter extended release, that was faithfully modelled, but a lot of people found they couldn't hold the aircraft on the brakes while performing the auto feather test, which is something we'll look at in a minute. So there's an amended script for that, and it arms the system at a lower RPM. So under normal operations, once that system is armed, it will detect if either of the engines falls below 20 psi on the torque while the power lever remains advanced. And if it detects that condition, it will do two things. It will immediately, well, it won't immediately, there'll be a 2-second delay, and then it will automatically feather the engine on which the torque's dropped to below 20 psi, and then it will importantly inhibit the auto feather on the other engine. And of course, the purpose of that is we don't have to muck about with feathering the engine manually in an emergency situation. We can do other things that we need to do to keep the aircraft flying. Now, we can test that on the ground. There is a system designed for testing the auto feather operation. So testing the auto feather system, first thing we're going to do is we're going to flip on the auto feather test switch. We're going to select the auto feather system. Then I'm going to arm the system by advancing the power levers until it arms. Okay, so the system's armed. We've got 30 odd psi on the torque gauges. Props are at 100%, and I'm going to simulate an engine failure by retarding the right hand power lever to idle. And there you see that right hand prop is feathered, and the system's disarmed on the other engine. So what should happen is when we pull the other power lever back to idle, the feathered engine should unfeather. And there it goes, the prop RPM on the right hand engines come back up to about 60%. And that's the auto feather test. In fact, the only thing that the auto feather test switch does is it inhibits the micro switches on the power levers that detect when the power lever is retarded. And so that tells us the auto feather system is going to work if we need it. Incidentally, in real life it makes a difference which engine fails, and that's due to another prop effect. A rotating propeller is inherently asymmetric, and when the relative wind is inclined to the propeller, so when the aircraft is pitched up or pitched down indeed, the thrust axis of the propeller is displaced inboard or outboard due to an effect called P factor. And because in this aircraft, as in many twin engined aircraft, the propellers rotate in the same direction, the effect overall is asymmetric. Now the detail of that is on this aircraft, because the props rotate clockwise, the effect means that the thrust axes are displaced out towards the right, and the net effect of that is that if we lose the left engine we get a much bigger yaw, or significantly bigger yaw, than if we lose the right engine. Now my experiments suggest that this is not modelled in FSX, although you will find P factor on the realism menu. It looks to me like that only really applies to single engined aircraft. So we're not going to say any more about that. Okay, so let's go to Harvey Bay. In fact we'll fly overhead Bundaberg and then on to Harvey Bay, and we'll land. What you probably won't notice unless you're eagle-eyed is I've switched into the amphibian for now, for reasons which will become clear. But we'll get to Harvey Bay, we'll probably land on the water, and we'll take it from there. Just before we go, something else to say about short takeoff and landing stall operations. Now we can't just push the power levers all the way forward to the firewall and take off. And as I said earlier, on the 300 series, if we did that, we'd be risking catastrophe in the event of an engine failure, and of course we'd be putting extra strain on the airframe and the systems, and we'll risk over-torquing or over-temping the engines, because these engines are derated. Of course, with the Twin Otter extended package you do get the 100 series as well, and you know, in one sense, if you want more of a challenge, it's worth flying the 100 series because it has the original PT26A 21 or 20 engines with 550 horsepower, so they're not derated, and of course you don't have anything in reserve, so it's more challenging to fly. The other thing which I didn't mention earlier about derated engines is if you're taking off from a higher strip, so the density altitude is higher, the engines can continue to make the full rated power in spite of the thinner air. These are normally aspirated engines, don't forget, on a turboprop, so there's no turbocharging, which means that performance is going to decrease with altitude. So if you've got all that excess horsepower in reserve, that stands you in good stead. So anyway, I'm not going to go on about that at great length. So we're not supposed to just, as I say, ram the power levers to the firewall and take off. What you're supposed to do is you're supposed to read the takeoff torque from this chart. This is from the flight manual. You read off this torque setting that's appropriate according to the outside air temperature and the pressure altitude and the airspeed that you're planning to fly at. I mean, in practice, in the simulator, you can do, you know, the obvious thing, which is you can advance the power levers until you get to the torque red line or the T5 red line, or shortly before it. You're not supposed to do that. It says in the book that you're specifically not supposed to do that. You're supposed to calculate the takeoff torque, but you know that works. It's going to keep you out of the red. If you go into the red, incidentally, you will get an engine failure sooner or later if you over torque the engines or over temp the engines. It's not instantaneous. In fact, if you want to demonstrate, I'm not going to do that, but if you want to demonstrate that you can ram the power levers all the way home and just leave the engines to overheat, and you'll get an engine fire sooner or later. The other thing you can do is you can dial in a high power setting with the power levers, and then you can feather the props, or one of the props, and just leave it that way for a while. So you'll see the torque go off the scale, and before long your engine will explode. So not recommended, but if you want to try that, you can do it. So we're just going to use the keep the torque and temperatures below the red line technique. Okay, let's get out of here. Let's just set up the GPS. We'll put in a direct to Bundaberg first, which is 21.5 miles away. Just put it on the GPS direct to. We should probably backtrack and use the whole of the runway, but since we're demonstrating stall takeoff, I guess we wouldn't be doing stall work with an amphibian from the grass strip generally, but you know, in the interest of dramatic license, we're going to get away with that. Okay, so let's have the auto feather system selected on. We've got the flaps down, and we're ready to go. Okay, auto feathers armed. Torque is pegged at just about maximum. Temperatures are okay. Let it go. There's VMCA. Whoa, that's bumpy. Okay, that's 400 feet ATL. Turn off the autofiller, get the flaps in. We're turning onto heading more or less. So I just wanted to make some comments on some of the things I've been covering in this video with respect to the props, and particularly to the feathering behaviour. What you're going to find is feathering is not fully implemented in FSX, and therefore in the Twin Otter Extended. So what you'll find is when you feather the props, it does affect the pulling power of the props, and so all the comments I made about efficiency and about fuel flow are generally relevant and do have an impact on the performance of the aircraft. But drag effects of feathering the propeller are not modelled at all. Now you can do your own experiments with this. You can go up to altitude, you can experiment with feathering or unfeathering while the engines are idle, and you'll notice there's no differential drag effect. You do get some transient effects while you're feathering or unfeathering the prop, but honestly that doesn't appear to be, to me it doesn't behave logically, it doesn't do what I expect it to do, and it is only transient. So once the prop's feathered or out of feather, you know, the net drag doesn't seem to be any different whether the prop is feathered or what pitch the prop is set to. And that really renders, you know, quite a lot of the stuff we've talked about irrelevant, particularly the need to feather an engine at all goes away if you have an engine failure, and that in turn renders the entire auto feather system redundant. So again, you know, you've got this thing that appears to be simulated in a lot of detail, and you can go through the motions of doing the tests for the auto feather, you can go through the motions of selecting the auto feather on and off during the takeoff, but you don't need to. Alright, so Harvey Bay, we're just looking for somewhere to land. We're probably flying quite illegally around the airport vicinity here, but you know, this is a simulator after all. There's the airport, but we're not going to land on the airport, we're going to land on the water. So the last thing we're going to cover on the props is something that's specific to the float version, and we're just on the water at Harvey Bay here, so we're going to talk about that. And this is the start locks. Now the problem with water operations is normally when we shut the engines down, the props feather when the oil drains out of the governor in the prop hub, and that's a problem when we come to start up, because as the props unfeather, they go through coarse pitch all the way to fully fine, but we get thrust on startups, and thrust on water, you know, unless we're moored to something, we're actually going to move, and we're not really going to be able to control that. And actually we get thrust on shutdown as well as the props gradually feathered. So to get around that problem, it's possible to have things called start locks fitted, and what happens is when you shut down the aircraft with the start locks enabled, the props go slightly into reverse pitch, and then some locking pins, using a mechanism I don't really understand, engage, and basically that latches the props in the fully fine position, and even when the oil drains from the hubs, the props don't feather. And that's great on shutdown because we don't get any residual thrust as the props move through course into the feather, and on startup we don't get any forward thrust either. So we're going to try and demonstrate that. Well, the first thing I'm just going to do is I'll just remind us what happens when we feather a prop. In fact, what I'll do is I'll shut down the right hand engine and feather the prop first, which is a normal shutdown. We'll just watch the gauges. So we're going to feather it. Torque goes all the way up to 35, approaching 40 psi. RPM goes down to 20%. Shut down. The RPM drops to 0, torque to 0. And if we were to look outside, we'd see the prop is feathered. So I'm just going to start that up again. Now if you watch the boat here, as we come out of feather, in principle we get a bit of a surge and we should get some movement. Now actually nothing significant's happening there. So that, you know, the reason we have start locks is that when we do that start up and the prop comes out of feather, you know, the thing's going to run away with us. Now that doesn't really seem to happen. We'll look at that in a little bit more detail in a minute. But what we're going to do is we're going to shut down both engines, this time with the start locks engaged. We don't do anything particular to engage the start locks. We just leave the props in the fully fine position and we pull the power. So if we do that, watch the boat and watch the prop RPM levers, gauges. Here we go. Torque's gone immediately, props simply go all the way down to 0. We're rocking because we're on the waves, but no significant movement as the props go spin down. Now in practice those prop gauges would wind down slowly because the props take ages to spin down when they're not feathered. That doesn't happen in the sim, but we're not going to bitch about that. The other thing you're going to notice if you look carefully is we've got beta indications here. Now that's because when the blade latches or the start locks are engaged, the mechanism puts the blade slightly into the reverse position, then it latches them into that position. and so we have the beta range indications. So what we'll do now is we're going to start up each of the engines and we'll see how that looks. So we're going to start the right hand engine first, again using this boat as the external reference. Okay, fuel pump on, spin it up, stable of 12%, put the fuel in, props go straight up to 100% RPM, torque is coming up, it's stable at about 5%, and we're not getting any lateral movement, so we can gauge from that there's no thrust happening. We've still got the beta indication, and in fact we'll start the other engine first before we talk about that. So now if we do nothing else and we try to engage power, nothing's going to happen because the blades are still latched in that flat pitch. In fact, something will happen. We'll get a silly sound effect. I'll just do that to demonstrate.
I forgot to disengage the start locks.
Yeah. So that's just a bit of comedy there. What we need to do is to disengage the start locks is we need to pull the power levers slightly into the beta range and then out again. On my system I've got two separate levers for that. Pull them in and the indications are gone. So now we're hot, we can apply power and we should start to move. Now that's all very well, but that wasn't really a very convincing demonstration of why we need the start locks. You know, even starting up with the props feathered, you'll see there wasn't any significant movement there. So it's another one of those things that, although it's simulated, it's not really worth having. In fact, we do get some residual thrust effects, and the best way to check that out is to put this amphibian on a hard runway, and we'll just have a quick look at that. Okay, so we're back on dry land. We're at Harvey Bay on the ground this time, and what we just do is we just go through that again with the start locks. We're going to shut it down, and just this time we're interested on the outside view. I'm going to leave the brakes off, but we're in the amphibious Twin Otter, so we've got start locks. And so we should be able to see whether we get any of those residual thrust effects. I'm going to feather both props. You can see we get some residual thrust there as the props go through into course. I'm putting my feet on the brakes now. We take the fuel away. So we've shut down, we're on the amphibian, but we haven't got the start locks engaged. We're going to start up the right hand engine first, just to see if we get any thrust as it unfeathers. So props selected, fully fine. Right hand engine, spin it up. Fuel in. Watching that engine unfeather, and we do get some forward and slightly to the left. I'm braking now. Okay, brakes off. We're going to do the same with the left hand engine. Spin it up. Again, watching outside. No brakes, and we're going forward, slightly slewing to the right, feet on the brakes. So we do get some start-up thrust, which is just noticeable on land if we have the brakes off. So now we'll shut down with the start locks engaged, and then we'll start up again and see what the difference is. So leaving the props fully fine, chop the fuel. We get the beta indications, the start locks are engaged. everything's spun down. So same experiment, we're going to start the right hand engine and we're going to watch outside, see if we get any thrust. Okay, looking out the window, there's the engine coming up. No brakes, nothing happened, no movement. So that simulation is having an effect. We're going to do the same for the left hand engine. Looking out the window, props all the way up to 100%. You can't quite see the gauge here, I can see it. And there again we get no movement. So there's definitely that simulation of the start locks has some effect, but you know, you have to question whether it's really doing anything worthwhile, given that the startup thrust without the start locks on the water, you know, it's pretty negligible. So there it is. That's just about everything to do with the props in the Twin Otter Extended. For completeness, there's one more test you can do. Prop governor overspeed test. So if you flip that switch to on, advance the power levers, all that happens is you should see after some oscillation the prop RPM stabilizes at 70%. That's a pre-selected test setting that the governor test switch imposes. Again, it's really a bit of fluff. If you want to do the checklists in detail, you can do the prop overspeed test. It doesn't make any difference to flying the sim. You can't overspeed the prop. You know, there's not simulated. There's no sense in which that is simulated. So there you go. I think I've covered everything.